well. Okay, record is going. I want to go ahead and welcome to the Eureka, Texas, February 2021 speaker series, mobile mappings, the GeoSlam technology, LIDAR capture for GIS workflows. We're very pleased to have Brian Rosensteel, and he is going to do the presentation today. Brian has 10 years plus experience working with 3D laser scanning, LIDAR, mobile mapping, reality capture, 3D modeling, BIM, CAD, etc. He's also one of the GeoSlam technical leads to introduce folks to the GeoSlam software. So, Brian, we're going to go ahead and turn this over to you, and we appreciate you having and having us and sitting on our platform today and talking to our folks here. So, go ahead and take it away, and we appreciate it.
All right, that sounds like my cue. Hopefully everyone can hear me all right. I'd just like to start off by echoing the thanks as well. Thank you for everyone who's attending today. It looks like we have a pretty good audience, and it's always a pleasure for me to have a chance to present in front of so many professionals all at once and get this information and this technology out to a wider audience. So it's something that I've advocated for and been a big supporter of this technology for years and years, and it's always great to have an audience to present to. So I'd like to thank you guys all for joining. I'd like to, of course, thank Eureka, Texas for inviting me to speak, it's really an honor to be here. As I mentioned already, the topic for today's webinar is going to be mobile mapping with SLAM technology, LIDAR capture for GIS workflows, and presented by myself and GeoSlam, which is the company that I work for. A little more on that in the next slide. So just a brief introduction and some background on myself before we get started. I am a senior solutions architect with GeoSlam based in the West Coast. I live out in California. My role with GeoSlam essentially is one of technical sales, so supporting our sales pipeline from the technical side, supporting workflows, technology integration, speaking to current and prospective customers and showing them the path to integrate this technology into their current workflows and whatever software platforms that they're using, executing training, doing demos, performing webinars like we're doing today. Some brief background on myself. I graduated from Purdue University with a bachelor's in computer graphics technology and a minor in art and design. Some of my professional experience includes material handling industry and technology, rendering and 3D animation, building information modeling, 3D laser scanning, surveying, mapping, and scan to BIM software and workflows. Some of the industries that I've worked in throughout my career are material handling, construction, architecture, engineering, real estate development, technology, and I should also list on there LIDAR and scan to BIM services as well, both as a professional and a part of the company. You will notice based on this description that I do not have a background in GIS. However, my role at GeoSlam, I regularly work with GIS professionals who are customers, dealers, resellers, internal staff at GeoSlam. So I've learned a lot about the industry and GIS workflows through my current role. That being said, I by no means consider myself an expert in GIS, so please forgive me if I do misstate or accidentally say something incorrect during this webinar today. Feel free to email me and correct me afterwards. I'm always willing to learn more as I go. My role with GeoSlam does focus on technology as it relates to sales, but I was asked by Eureka to give a strictly technical webinar today. So I'll try to focus on the technical side of the technology and not so much on selling you on any one specific solution, GeoSlam or otherwise. So the majority of the content, is going to relate to GeoSlam, as I am a GeoSlam employee. So you don't be surprised if you do see a lot of our products on these slides and data from our products on these slides. But rest assured that I'm generally an advocate for all mobile mapping technology and have been an end user of it for several years. So that being said, let's get into it. So this is the agenda for today's webinar. Lots of different content here. First, we're going to talk about SLAM technology as a whole, what it is, how it works, and also a brief history of kind of where it came from and where it's going. And then we're going to talk about what we can capture with this technology. and take a look at some examples of the data. There'll be lots of images of sample data. If we have time at the end, I'll even bring up a live demonstration of some data that I captured just recently, but time permitting. So we'll keep an eye on the clock there. And also talk a little bit about kind of at a high level how we can use this data, what kind of applications and workflows and software we can integrate this data into in order to derive value out of it. Then we'll talk about comparing solutions. So there's all kinds of different SLAM-based mobile mapping tools out on the market of various price points and different levels of integration and with different focuses. So kind of navigating that world of comparing what's out on the market today, and also comparing mobile mapping systems to other LIDAR systems as well, such as a static LIDAR system or an aerial-based LIDAR system. Then we'll talk about some of the advantages and disadvantages of SLAM technology. With any kind of technology, there's the good, bad, and the ugly. So we'll talk a little bit about what those look like and kind of comparing and contrasting between different other types of LIDAR systems that are out there. And then very importantly for GIS workflows is tying your data into coordinate systems. So we'll talk about the different workflows around georeferencing data sets and assigning them to maps and that sort of thing, and a couple examples of those. And then kind of the meat and potatoes of the webinar today is going to be talking about who's using this technology and what are they using it for. We'll go through some use cases that relate to GIS industry specifically, and things that are kind of on the outskirts of the GIS industry. And I also have a case study. And like I said, I might be able to show you some data at the end, time permitting. And then the kind of last section is talking about the future of this technology. As somebody who works in the industry, I can sort of understand the trajectory of where this technology is going and some of the key points of where it's moving in the future, both internally at GeoSLAM and externally with all of our competitors and new products that are coming on the market every day. And then lastly, we'll finish up with question and answer session, and that will be moderated by Ollie and Brian. So as we go through this, if you have questions, if anything comes up, feel free to enter those in the chat window, and then we'll address them at the end. We'll try to get to all of them, but of course, time permitting. All right, so first section is SLAM technology. What is it and how does it work? So SLAM is an acronym. It's a very important acronym to companies like GeoSLAM. We incorporate it in our name. It's kind of the foundation of all of the technology that we develop. But that acronym stands for Simultaneous Localization and Mapping. And essentially what that is it's an algorithm. And there are hundreds of variations of SLAM algorithms out there, and they're all kind of different and specific to specific technology and have different applications and things like that. But essentially what all SLAM algorithms do is they answer continuously two questions. And those questions are, where am I in a given environment? And what does that environment look like? And we're kind of doing this cyclically. So we're continuously answering those two questions based off of the raw data that we're getting from the sensors that are incorporated in the instrument. And then basically by answering these two questions, we can essentially map an environment as well as track our position or our trajectory path through that environment. The resulting data from this, at least specifically for the purposes of 3D mapping, are millions of data points in an XYZ coordinate system that we typically call a point cloud. This is an accurate three-dimensional representation of the environment based on a dense collection of data points that are captured typically from a LIDAR sensor. Another possible output would be a three-dimensional mesh, can be the result instead of or in addition to a point cloud. So some SLAM out there is more heavily used for tracking trajectory path and location, and mapping components plays more of a backseat. This may be used for things like obstacle avoidance, collision, those sorts of things. SLAM was actually developed around the robotics and autonomous vehicle industry. So that's kind of how SLAM relates to those industries specifically. But what we're going to focus on in this webinar is how SLAM technology focuses on the mapping industry, where the trajectory and positional data play sort of more of a backseat role, while the 3D data is really more of the star of the show. So how does SLAM work? Sorry, this animation is not what I wanted it to be. So basically, at kind of a high level, the way that SLAM works, or this diagram kind of illustrates how SLAM works. As I said previously, there's many different types of SLAM. So it's quite difficult to sum up all of them into one concise, clear chart, but this is my attempt to do so. So of course, I'm most familiar with how GeoSlam's SLAM algorithms work, but there are kind of some universal components and methods that can be generalized, and that's essentially what I'm doing here. So SLAM starts with raw data collection from various sensors. The type and number of sensors used varies from product to product or SLAM algorithm to SLAM algorithm, and each system's unique SLAM algorithm. But I've listed some of the most common ones here. So you can almost always find a 2D or 3D LIDAR or range finding sensor within a SLAM system. That's typically how we're producing the mapping data. There is such a thing as visual SLAM, which is created completely from cameras or pano imagery, but that's less common and also less accurate. Another thing we commonly find in SLAM-based mobile mapping systems are inertial sensors. So an IMU, inertial measurement unit, a tactile sensor, or leveling type sensors, or a lot of times all of these things are combined into kind of one sensor. A lot of times we refer to that as an IMU just by itself. Also based on SLAM, a lot of times we're integrating cameras, either kind of flat cameras, wide angle cameras, or 360 pano cameras. Sometimes those cameras are integrated into the SLAM processing. Sometimes they are integrated more into the post-processing and stitched into the data after the fact. But as I mentioned, there is such thing as visual SLAM, which uses 100% visual data from cameras in order to do SLAM, kind of like a real-time photogrammetry type solution. Other types of external miscellaneous sensors that you'll find in mobile mapping systems are things like GPS, Wi-Fi, not so often anymore, radio, not so often anymore, but sort of in the early developmental phases, those were used a lot for that multi-angulation step. Things like sonar, radar, and RTLS have also been used in some cases, but are much less common. So essentially the SLAM processing happens in this algorithm, and the way that SLAM algorithms kind of generally work is we take that raw data and we perform various secondary processes on that raw data, such as feature recognition, which identifies surfaces and objects within the data, positional trajectory, which is a rough calculation of position change over time, usually coming from an IMU or possibly visual sensors as well. And then multi-angulation to reassess positional accuracy, and cloud registration, which fixes any kind of misalignments and continues to update the position relative to features that are based on the 3D LiDAR data. So each of these secondary processes kind of informs all of the other processes, and this runs in some sort of a cyclical algorithm with multiple iterations, usually hundreds of iterations, basically until we reach accuracy tolerances and or diminishing residual returns. And this is essentially how most SLAM algorithms work. But again, there's a lot of variation from product to product. So basically the end result of the data is a accurate, registered, unified, three-dimensional point cloud and or 3D mesh, as I mentioned earlier, as well as an accurate registered trajectory or positional data path. Usually both of these resulting data sets will get written into universal file format so that they can be read by pretty much any software that's capable of consuming and working with them. Below, we also have a graphic that shows what SLAM can kind of look like in real time. This is actually based on the GeoSlam SLAM algorithm. So essentially what we're doing is we're calculating initial position and we're calculating initial data around us, so initial surfaces around us. Then as we move, the IMU is roughly calculating our trajectory. It's not terribly accurate all by itself, but It's able to roughly calculate that trajectory. And then we match surfaces in the 3D LiDAR data and use those matched surfaces to basically update the trajectory. This is basically what we call real-time SLAM or local SLAM. But there's also such thing as global SLAM. So global SLAM is like a second iteration of SLAM that accounts for loop closures and data redundancy, and has the ability to kind of mitigate or fix any error that might be accumulated by local SLAM. So both of these things together can produce really accurate point cloud results. Sometimes we also use like external sensors like GPS or coordinate points or control points, something like that, in order to achieve that global accuracy in lieu of using global SLAM. Sometimes that's not the easiest process for different applications. So I know this is a little in the weeds, but hopefully it gives you kind of a high level understanding of how SLAM works. Again, this doesn't really represent a specific SLAM algorithm, but more of a generalization of how all SLAM algorithms are able to work. Oh, some more animation stuff. So also brief history of SLAM technology and kind of how it originated. So SLAM can primarily trace its roots back to the robotics industry in the 80s and 90s. Robotics engineers basically wanted autonomous vehicles to be able to move around without bumping into walls, people, each other, basically that obstacle avoidance and navigation. Being indoors, they couldn't really rely on GPS for navigation. So they started using these other kinds of sensors like LIDAR sensors, range finding sensors, things like that. So they essentially, as a result of this, designed an algorithm that could concurrently map and navigate by using these various sensors and the raw data that comes from them. So SLAM was born. So essentially, SLAM technology was initially widely used by this autonomous vehicle robotic industry, and the mapping data was sort of used on the backseat to do navigation, obstacle avoidance, collision, but it wasn't actually produced as a deliverable. It wasn't really something that anybody would see. And it also wasn't really all that accurate by itself. So it wasn't all that useful, except for to the robot that's using it for navigation. But as SLAM mapping accuracy continued to increase and improve, and the accuracy continued to improve, the resulting map was then able to be used for various applications. And that's essentially what we're talking today, the mobile mapping applications with SLAM technology. So hopefully that kind of makes sense on how that technology developed over time. So the most important thing is, the technology is great. It's important to understand how it works, but it's very also important to understand what we can do once we have that data, and what does that data look like, and what is it, what can we capture with it, and what can't we capture with it. So the next section is just kind of talking about the types of things we're able to capture with LiDAR data. And this is actually as a whole, this isn't just specific to mobile mapping systems, but mobile mapping systems are part of these issues as well. So what does the data capture? Well, it captures things that are solid objects, things that are non-reflective. The more matte, non-shiny an object is, the cleaner it captures. Sometimes really dark surfaces like matte black surfaces also can create more noise and things like that in the data. We collect foliage really, really well. So this is a really common application is in forestry. And I'll actually show an example of that later on in the presentation. Capturing things like hardscape, so curb lines and pavement, things like that, captured really, really cleanly with LiDAR data. Landscape as well, and then architecture, structural, kind of anything inside or outside of a building tends to capture really well, as well as utility lines. So kind of generally set a threshold for capturing objects of an inch and greater. Anything bigger than an inch captures really, really well. Things that are smaller, you might capture them, but you're not necessarily going to get really accurate data on them. And this refers specifically to mobile mapping systems, and kind of get into the differences between mobile and static systems down the road. But things that the LiDAR does not capture well are water, any kind of see-through surface, Of course, underwater, while there are actually underwater mapping systems, bathymetric systems that are loosely based on SLAM, that's not what we're talking about in this presentation. Again, reflective, shiny surfaces, glass, mirrors, those types of things. Moving objects as well, it actually captures them a little bit too well. So we get a lot of noise and what we call ghosting in data when objects move through the scene as we're mapping it. Like I said, really small objects, anything that is an inch or less is going to be kind of hard to accurately depict or measure within the data. See-through objects like glass, any object that is from a really sharp angle of incidence. You'll see this as you scan up the side of a building as objects get further and further away from the building and higher up, that angle of incidence gets sharper and sharper, and the data gets less and less usable. And then also things that are far away, so out of range. Every system has an actual range and a usable range for the data. So the good news is that most of this kind of bad data or unusable data can be filtered out in post-processing. So a lot of times you don't have to mess with it. In very rare cases, these types of things can affect SLAM algorithm and accuracy and things like that, but I would say that's not typical. So example of what the data looks like. This is kind of an overview collage of different point clouds from different systems and different software packages. With this technology, you can capture data in virtually, pun intended, any environment, any subject matter for many industries, applications, and workflows. If you take a step back and you kind of think about the applications of this technology and the possibilities become almost limitless. And as SLAM-based mobile mapping technology continues to improve, accuracy continues to improve, the systems become easier to use, the systems become more cost-effective and more kind of consumer grade, the possibilities continue to open up exponentially as the technology expands and improves over time. This webinar today, we're going to focus on GIS, but really with some small tweaks, this presentation could be easily directed towards 100 different industries. And that's one of the really exciting parts about my job, is that I get to talk to people in all kinds of different industries with all kinds of different problems that they're trying to solve with this technology. And I get to show them how to solve those problems, hopefully. You know, one day I'm scanning underground in a mine, and the next day I'm scanning in a forest from a UAV. All with the same technology. So this technology is extremely versatile. It can be applied to all kinds of different industries and applications. And then, of course, what can you do with the data? So we said that, you know, we're able to capture the data. You know, it's almost limitless possibilities, but the same can really be said about what we can do with the data. So point clouds are now becoming very widely accepted by CAD platforms, 3D modeling platforms, mapping platforms, and other similar tools. With these third-party tools, we can use the point cloud to do some pretty impressive things, like measure literally anything based on distance, area, volume, etc., of any element in the data. We can create three-dimensional models. We can create 2D vector line work. And there's also many tools on the market now, and this is a really hot market for automating these processes, is what we call scan to CAD, scan to BIM automation. And those can really simplify, speed up, and increase the overall accuracy of the process and kind of take the human element or the human error element out of it. These images kind of illustrate just some of the many examples of what we can do and produce with point cloud data. So on the top left, we have some point cloud data integrated into a mapping tool. On the top right, we have some mobile data that is mapping a street and extracting curb lines and elements around the roadway. We can map entire cities. You know, we could theoretically scan inside and outside of every single building in a city and have an entire virtualization of, you know, an urban environment, a campus. Some college campuses have even kind of pursued this as something that they're trying to produce internally. And then, of course, that kind of scan to BIM, scan to CAD workflow, where we can take this 3D data and convert it into a 2D or 3D CAD model. So that's an example of that down at the bottom right. So the next section is comparing these solutions. There's all kinds of different SLAM-based mobile mapping systems on the market, and it can be kind of difficult to navigate. Of course, I'm a little bit biased towards the systems that my company produces, but really each system on the market today has its pros and has its cons. And I always try to guide my customers to pick the best solution for their work, their job requirements, their specifications, accuracy requirements, and of course, budget is always a big component. So there's really no such thing in my mind as a perfect mobile mapping solution or a one-size-fits-all mapping solution. Some systems are more modular than others. Some are more specified to specific applications and industries. But in this section, we're going to kind of look at comparing mobile mapping solutions to one another, as well as comparing them to other similar like LIDAR solutions, such as using like static scan. So this slide is all talking about different types of SLAM mapping systems, and I've kind of categorized them into these 8 different groups. There's probably a few more, but these are kind of the main ones that we see on the market today. So vehicle-based mobile mapping is kind of the original mobile mapping. Some of the first systems, SLAM-based systems, were designed to be mounted on vehicles. Nowadays, they are either integrated into the vehicle themselves, or they are mounted to a vehicle and are kind of a standalone system that can be mounted to just about any vehicle and driven around with. There's also handheld. That's one of the categories that GeoSLAM really specializes in. Those are very modular. They're very easy to use in all sorts of different environments, scan in confined spaces, scan indoors, outdoors. You know, they allow themselves to be quite versatile. There's aerial UAV based systems, and sometimes handheld systems or other type systems can be mounted to a UAV and flown with. There's backpack systems, so you know, that integrate cameras and are basically more of a mobile version of a vehicle-based system. One of the most or the biggest markets that we're seeing develop right now in the industry is mounting these to robots. So one thing that GeoSLAM does is we talk and partner with a lot of the robotic companies out there that are interested in integrating mobile mapping into their system. So it's kind of cool how the technology has come full circle. Kind of started in that autonomous vehicle industry for navigation, and now it's coming back and being integrated for mapping as well as navigation, kind of in all-in-one solution. So this is something to definitely keep your eye on in the future. Also, one of the more original types of systems for indoor use is cart-based mobile mapping. Again, kind of integrating all of that stuff that we can put on a vehicle or on a backpack on a cart and make it easy to kind of push through an environment. There's some limitations to this, but it creates really more clean data because you have almost more of a fixed elevation the whole time that you're scanning. And then we have you know, fully integrated systems that kind of have everything all in one versus modular kind of hybrid, like kind of you know, you can swap out components and that sort of thing. So integrate different cameras, integrate different sensors, those sorts of things. So kind of a differentiation between a fully integrated system and a modular system as 2 separate kind of subcategories. And then some of the criteria that I would recommend using for comparing these mobile mapping systems are points per second. So that's going to dictate how many points we're able to scan in a given amount of time. These systems, you know, originally were scanning tens of thousands of points per second, and now they're scanning hundreds of thousands of points per second, and really dictates the kind of level of detail and level of density you're able to get within the resulting data. Range is also a big component, you know, especially if you're doing kind of outdoor longer range captures. You want to capture building facades and you know, utility lines and things like that. Range is going to become a factor. So understanding what that range is and what that usable range is as well. So you kind of have the overall range, like the max distance that the system can capture, and then you have the range that you can actually kind of use that data. It's dense enough and detailed enough to be able to use. So those are important to understand. Real-time versus post-processing. Some systems are able to process SLAM in real time, have onboard computing. Some systems, you take the raw data and you dump it into a computer or software tool, and it does the processing on the back end. Processing speed and simplicity also kind of ties into that. So how plug and play is the processing? Is it something that you have to do a lot of manual intervention on, or do you just feed it raw data and it kicks out usable data set? Understanding the limitations of the system. So I mentioned things like, a cart-based system has limitations indoors because it doesn't do elevation changes very well. You can't go up and down stairs with it. So kind of understanding where those limitations are and if those are going to have a negative impact on the work that you're doing. Ability to modify the SLAM algorithm is another big component. Some systems are more of that black box solution where you just feed it data and it kicks out a result, and that data is either good or it's not good. And if it's not good, you have to start over again. Whereas some systems allow you to adjust and modify SLAM processing to fit your application, to fix any kind of misalignments or issues that may come up with the data. So that can be an important component for a lot of people. Some people want that kind of plug and play solution, black box solution. Some people want full control. Some people want the option to choose one or the other. So that's a big factor. Real-time viewing. A lot of systems have the ability to use a tablet or a screen to view the data coming together in real time. I would say this is never really necessary, but a lot of times it's really helpful when scanning and viewing the data coming together and kind of giving you that quality assurance that everything's working properly and your data is coming together without any issues. Imagery is something I mentioned a couple times, but the ability to integrate imagery and use that imagery to colorize the point cloud, and then the quality of that resulting colorization as well. So if colorizing data or integrating imagery into your data is important to you, it's really important to understand how these play into the system and what level of detail and accuracy you're able to get with the imagery sensors that are integrated. Different types of sensors, just understanding what these sensors are, what they do, how they impact the data, and how they can be modified in order to reprocess or fix data. And then, of course, the big one really is global and local accuracy. With a mobile system, you kind of have two levels of accuracy. So global accuracy is the accuracy that you get from one side of the scan all the way to the other, and then a local accuracy is more like those micro measurements. So measuring the width of a room or a door, or circumference of a pole or something like that. Those are more of those local accuracies, and those are different for all systems. So understanding what those are is going to be really important. So this slide is a graphic that kind of compares static scanning to mobile scanning, and understanding what the time difference and accuracy difference between these two situations are. So we did a head-to-head comparison, scanned at the same space. I think it's roughly a 15,000 square foot office space with both systems. With the static system, we took 125 scan positions. Each scan was about 2.5 minutes. That also includes time to reset the scanner. So about a little over 5 hours of total field scanning time. And then roughly on the back end, we're spending about 6 minutes doing post-processing, registration, QC, and exporting data, basically the total process to take that raw data and turn it into kind of a finished usable point cloud to be used in a third-party software. That all in was about 12.5 hours of total time. So total time to create a point cloud with a static scanner for this space was about 2.2 work days, 17.5 hours. So considerable amount of time. With that, we get a little bit better accuracy. So we get plus or minus 1 centimeter of global accuracy. Again, that's a measurement from one side of the data all the way to the other, basically the accuracy of how well we're able to stitch all of the data together. And then a local accuracy, kind of that micro accuracy of a couple millimeters. With a mobile system, we're doing one continuous capture. So the total time to capture with a continuous capture was 30 minutes. So 30 minutes all in field scanning, and then about 45 minutes of post-processing, registration, QC, export. Again, all of that is automated. A lot of it takes place on board the system itself. In this particular case, that can vary a little bit depending on system, but I would say typically you're looking at maybe 1-to-1 to 1-to-3 times the scanning time. So a 10-minute scan can take anywhere from 10 to maybe 30 minutes to post-process and perform registration and export to a universal format that you can use in a third-party software. So all in with the mobile system in the same space, we're looking at, just a fraction of a day, and you're sacrificing a little bit of that accuracy, but it's really only a couple centimeters versus 1 centimeter, and a local accuracy of a few millimeters versus a couple millimeters. So in my mind, it's kind of a small sacrifice of accuracy for a big gain in time efficiency. So we'll talk about some of the advantages and disadvantages of using a mobile system. Like I said, there's no kind of perfect solution. So there's always kind of pros and cons. Some of the biggest advantages, as you saw in the last example, are speed of capture, ease of capture. You're automating a lot of that processing and stitching. It's not really difficult technically to put this data together. It's basically dropping it into a program and letting that process. Imagery integration is also very seamless and sometimes can be fully integrated. Accuracy is pretty good compared to traditional survey methods, compared to doing things like using a tape measure or using distos and things like that. It can be even better accuracy and less manual. Also level of detail, of course, you're getting a much more data-rich output compared to a traditional survey. Some of the disadvantages to using this technology, this is mostly compared to a static LiDAR system, is you're going to get noisier data. You're not going to have as long of a range with your typical kind of one-to-one comparison. You're going to have lower fidelity of colorization, so you're not really going to get that photorealistic kind of clean colorization like you might get with a static scanner. It's going to be a little bit rougher. You're going to get a unified data set. So some people really want control of all those individual positions and the ability to edit all of these individual positions. So with the mobile system, you don't really have that ability. You're just going to get kind of a lump unified data set at the end of it. You have limited ability to modify the data. So basically what you capture is what you capture. Accuracy, of course, you're going to sacrifice a little bit of accuracy compared to static LiDAR, as well as level of detail compared to static LiDAR. So making that decision between the two, is something that you kind of have to weigh back and forth, pros and cons. So these are kind of situations where you would use a mobile scanner versus where you would use a static scanner. So mobile scanner is a situation where you need to cover a large area, you need to capture data quickly, you need to use the data quickly. Maybe you're in kind of a difficult or hazardous environment with the current pandemic going on. Mobile systems have an advantage because you're kind of in and out in no time, and it's kind of a non-invasive capture technique versus a static scanner where you're spending a lot more time in a space and kind of getting in people's way and that sort of thing can cause some issues. Shorter range is okay, lower point density is okay, level of detail and lower accuracy is okay as well. So all of those things kind of can be hangups with the mobile system. Versus a static system is really we have a smaller, more detailed project scope. You have lots of time to capture, you have lots of time to process data. You're kind of in a low traffic environment, so you don't have to worry about the system being invasive to what's going on in the environment. You really need that clean data. You really need that long range. You really need higher point density and level of detail. And you really need sub-centimeter level of accuracy to fulfill the scope of work. So in my mind, these are not in competition with each other. They really kind of complement each other. A lot of times you'll find applications where you could use both a mobile and a static system. You use the mobile system to kind of capture the low detail areas and the static system to capture high detail areas. And even using them in tandem, you'll be able to really save a lot of time overall to get a usable data set. Okay, so very important to GIS workflows is tying this data into real world or local coordinate systems. We call this georeferencing. I think that's a pretty commonly used industry term. There's really kind of two methodologies for georeferencing that I'm going to go through in this webinar. The third one would be more of a manual process of manually taking the data and moving it, within a third-party tool. So that's kind of the difficult and dirty way to do it, but there's some cleaner workflows. So the first one I want to talk about is georeferencing with control points. So basically in the field, we can capture reference points using physical targets like spherical targets, or some people use like cones and things like that to capture reference points. We can use checkerboard targets. Most LIDAR systems are able to capture variation in material. So checkerboard target, you basically position the very center of those. Sometimes those can be painted, or a painted X will also work. Sometimes people use tape and things like that as well. So really any kind of feature that you're able to see in the point cloud data can be used to capture a reference point. Also, some LiDAR systems, mobile mapping systems, will have an integrated ability to capture these. So with an integrated laser or a laser crosshair, or maybe even a physical crosshair that you're setting the system on and observing the point and calculating that offset from the ground or from a wall, based on that target's position. So we're capturing those reference points in the point cloud data, and then we're capturing control points in the real world, using kind of traditional surveying methods. That can vary widely. It could be a GPS system, it could be a total station, it could be, within satellite imagery, it could be based on current drawings and tying into current drawings. So there's a lot of different options for obtaining those actual control points, but you want to make sure that you're using same targets and the same positions for control points as you do for reference points. And then essentially on the back end, you're just assigning reference points to control points. Some software is able to do this kind of automatically. So, and then we can use a rigid or a non-rigid transformation. Non-rigid is basically gives you the ability to adjust SLAM based on those control points and kind of prioritize them, which can increase overall accuracy. So this is a pretty viable method. I kind of refer to that as more the traditional method for georeferencing. The other method is using GPS. So some GPSs integrate with SLAM systems, some kind of capture raw data, and then you assign the trajectories to each other and use the basically the GPS trajectory as your reference coordinate system. So this is kind of an overview of what that looks like. Capturing that rough LiDAR data in the field with its scanner trajectory, capture the GPS data in the field with its trajectory, and then use post-processing software to marry GPS and the scanner trajectory together and reference one to the other. Some systems are even able to do this kind of in real time. So it's integrated into the SLAM processing. It's most commonly found on the backpack systems or vehicle-mounted mobile mapping systems that are kind of fully integrated. So who is using this technology, and what are some of the most common applications that we're seeing it being used for, specifically that relate to the GIS industry? So this is really urban and roadway mapping is really one of the first types of SLAM-based mobile mapping systems that were developed, and still probably one of the most predominant in the industry. But they give you the ability to drive with a system and capture data at the same time, usually integrating 360 imagery with that as well. This can be accurately stitched, the imagery rather can be accurately stitched and oriented to the LiDAR data. And then of course we can also georeference using GPS or control points or manually in a mapping or a third-party software tool. Products like Orbit GT offer all of this kind of in one package, which really allows you to integrate this all into one view, which is pretty nice. And I'll show an example of that if we have time here at the end. The next generation of this technology is really taking all of these similar components and integrating them into a backpack system. And this allows you to capture really the same kind of data, but in environments where it's much easier to walk than drive, such as kind of a dense urban environment, campuses, amusement parks, those sorts of things. Basically anywhere that can't be accessed by road, you can easily access with the backpack. In that similar vein, doing utility mapping and survey, that is also typically done with backpack mounted systems, potentially aerial UAV mounted systems, and handheld systems would also work for mapping utilities as well. Typically, for this application, a GPS sensor is integrated for rapid georeferencing of miles and miles of data, mapping these utility runs. The same technique can be applied to really any kind of long distance scan, mapping roadways, mapping drainage channels, things like that. So the scan data is then brought into a third-party tool to do 2D or 3D CAD. And we see a couple examples of that here in this data. There's been a lot of progress made around feature extraction as well for utility industry specifically, as well as auto data classification. So instead of modeling the data or drawing the data, we're basically just using the raw data and classifying it based on what component it represents. Yeah, imagery, of course, is also a big component and can be integrated for visual reference and documentation for utility mapping as well. And then the next component is site mapping. So it's kind of on a slightly smaller scale, but sort of doing more or less the same thing. We can use a backpack system for this. We can use a UAV mounted system for this. We can use handheld system for this. And basically survey any kind of site once again, take it into a third-party application or CAD tool and be used to develop 2D or 3D site map, can create vectorizations. Feature extraction tools can also be used for this. We see applications to extract elements like curb lines, road lines, building footprints, other sort of similar line work in 2D and or 3D. And this is really kind of an example of a quick and simple way to produce highly accurate and rich site plans based off of LIDAR data. And the last one I wanted to mention is as-built documentation or scan to BIM CAD work. This really kind of moves us to the inside of the building. And primarily we're doing this type of work with handheld SLAM systems. And so we're capturing potentially both the interior and the exterior of a building, and then taking that data into 2D CAD platform or 3D BIM platform and being used to create accurate 3D informational models or 2D CAD as-built drawings. So these are a couple of examples of what we're able to do with data to do scan to BIM and scan to CAD applications. And then here, hopefully this will play for me. This is a video of a case study that we did in Singapore with the city of Singapore to map trees. So I'll just kind of let this play and I'll shut up for a second. So this is a really good example of how we can use backpack mounted fully integrated system to combine imagery and LIDAR data into a third-party platform. In this example, the data was being integrated into Orbit GT, which is a third-party application that GeoSLAM integrates with directly. So what does the future look like? It's kind of hard to say for sure, but being a professional in the industry and working internally for one of the primary manufacturers and developers of this technology, I can kind of tell you the trajectory paths that we're going on and what we see our competitors and other people, who are developing software and products around these solutions are doing. So The main things that we're going to see in the future are increase in automation. Automation is going to be really key. And it's going to be applied to areas like post-processing. So just really having a focus on feeding the post-processing software raw data and spitting out usable results. I think you'll see more of a focus on real-time processing as well, as opposed to doing post-processing on a computer and just feeding it raw data. You also see increased automation in data preparation and creating deliverables. So taking those point clouds and turning them into usable data sets that can be married into third-party platforms, really automating that process and streamlining it. Another automation point is in point cloud classification. So being able to automatically identify objects in a scene and kind of add value and data to what those objects are. So basically using a point cloud as a 3D model, as opposed to using it as an underlay to develop a 3D model or 2D line work. In that same kind of respect, we'll also see automation in feature extraction tools. So specifically in that kind of scan to CAD, scan to BIM industry, I think that what we'll typically see, or what's typically asked for in that space is really kind of the magic automatic scan to BIM button. So feed it a point cloud and it spits out an accurate 3D model. I know a lot of work has been done in this space, but it's still definitely something that's being developed. So look for that in the future. Of course, SLAM is going to improve more robust SLAM algorithms, which is going to make the data easier to capture, more reliable capture in the field, less issues of creating misalignments and issues in the data as SLAM continues to improve. Also with that, we're going to get increased accuracy, increased level of detail as we integrate higher end LIDAR sensors, and higher end LIDAR sensors continue to come on the market. Integrating additional sensors as well. Things like visual SLAM, I think, are going to become more predominant, especially in some of those consumer grade, cheaper options. Also integrating things like thermal imagery or full spectrum imagery to get some different data and information into the final data set. I also think we're going to see a lot more lower cost, easily accessible hardware options. Really common example that just came on the market recently is the iPhone 12 that actually integrates a LiDAR sensor. It can't be used for GIS workflows, at least not in my opinion, but it doesn't have the accuracy or the level of detail, but you can use it to scan a room or two in your house and maybe do a redesign of your kitchen or something like that. So I think we're going to see more and more of these kinds of consumer grade tools coming out that are a lot cheaper.
Hey, Brian, this is Brian. So yeah, I'm glad you touched on the new iPhone and the LiDAR sensors. We've got a couple minutes left here. I just wanted to talk to you. But I'm glad you touched on the future trajectory of the industry but yeah, just glad you touched on that. So, but I want to let you know we just have a couple minutes left here. I don't really have any questions in here for you now, but I just wanted to. Oh, we got one in here for you. Okay. Photogrammetry can generally do many of the same things as LIDAR. As I understand it, which LIDAR use cases provide the best justification for higher price versus photogrammetry?
Yeah, that's a good question. So photogrammetry is something that LIDAR, especially mobile mapping LIDAR systems, kind of compete with. Really, as I would compare those two, I would say that photogrammetry solutions are usually a little bit lower accuracy overall. In order to really get good accuracy with photogrammetry, you need to heavily integrate things like ground control points. So you have a sacrifice in accuracy, but you do get really nice imagery and photorealism with photogrammetry applications. So there's kind of a trade-off between those two. Also, photogrammetry doesn't work very well indoors. It's not nearly as versatile. Photogrammetry is usually used for aerial capture. Occasionally people will use photogrammetry for site mapping and things like that, but it is a lot more limited as to what you're able to actually do with that data and the applications that you can apply it to.
Well, we'll try to squeeze another one in here. If y'all have any more questions, go ahead and send them to us. And Eureka Texas, we'll pass them on to Brian, and we can answer them and then post them on our website. So Lucas has a quick question here. We're right at 1 o'clock. So compared to a Trimble static SX10, I see the benefit with speed of capture, but with the integrating into third-party software, how would that work? Currently using Trimble Business Center, and I think this is very similar to a question I asked you yesterday, Brian.
Yeah, it's a great question. It's a common question that we get. So the way that you typically integrate with any kind of third-party software is by using universal file formats. So the big ones are LAZ, LAS, and E57. There's also TXT, PLY, XYZ. There's all kinds of formats out there that are kind of universally accepted by third-party software. So if you're trying to integrate static scan data and mobile scan data together, really the best place to do that is within a registration tool like in Trimble Business Center, Trimble RealWorks, or like a Cyclone or Ferrocene, or any of those kinds of third-party registration tools. Some people even use like Cloud Compare to integrate this data together. But you just use universal file formats, and you bring this unified data set and you register to it basically like it's a scan, like it's a big static scan.
Well, very good. We'll get to some of the other questions here. One other person had what applications utilize these programs, but I think you answered some of that already. You got Trimble Business Center, LP360, any type of LIDAR processing. But Brian, I want to go ahead and thank you for a great presentation today. It was a lot of information, but extremely useful information. About SLAM technology. I want to thank my colleague and co-partner Ollie Powers for helping us out. Ollie, I'm not sure if you're still here with us, but say howdy. And is there anything else we need to cover, Ollie?
No, I think that's it. Thank you everybody for watching with us, and thank you Brian for that fantastic presentation.
Yeah, and we will be posting this on our YouTube channel shortly. We will be putting a PowerPoint presentation up on our website in case you need it. Any questions you have for Brian, go ahead and send them to our website and email address as you see it there on the screen. And we will see you again next month. Ollie, do we have the next one set up and ready to go, or
we do.
To announce?
It's live on our website, so you guys are welcome to sign up for it now if you'd like. We'll be sending out the emails for that probably sometime next week.
Okay, I think we were at 81 max capacity on people today. So once again, y'all stay safe, and we will see you again next month. And thank you for attending. Brian, thanks a bunch.
Thank you. Sorry for going over on time.
Oh, you're fine. You're fine. Okay, well, I will end the meeting.